Hello, y'all. Barry Lee Barry Jr. back for some more physics as promised. Um, I plan on, I'm still going to finish the sequence of problems I started yesterday. I was doing the homework one problems from Golds um, and working through the solutions to find out any things I need to correct. I finished looking over those earlier, but I'll actually work those out. What I also wanted to do was take a look at the new homework problems that are coming. So we have some new homework problems coming soon, also in Golds. So probably won't be able to do these right now, but I want to at least get an idea. So I'm scrolling right now. So the first one, which is 313. Yeah, 313. Gotta make sure I'm looking at the proper one. Yeah. So what I'll do, I'll go ahead and at least look over this problem with you and see how far I get. You know, I might be able to do it, but I doubt it. And if I can, I'll do it. If not, I'll at least get an idea. May even look at the second one as well and see if I can at least get started on that one. To see how many problems it is altogether. Let me see. 1, 2, 3, 4. 4 altogether. So we shall look at the first one, which is directly from the book, and see what I can do with that. So I have my screen shared momentarily. Go ahead and get. Oh, and those who show up, be sure to drop a line. Let me know if you have any comments. Like, subscribe if you haven't already. And all right, let's go ahead and get the party started. So this is what we're looking at. Question 313. And right now it's not giving me a horizontal slide. There we go. Boom. So it says show that if a particle describes a circular orbit under the influence of an attractive central force directed towards a point on the circle, then the force varies as the inverse fifth power of the distance. All right. So that for the orbit described, the total energy of the particle is 0. Find the period of motion. Find x dot, y dot, and v as a function of angle around the circle. And show that all three quantities are infinite as the particle goes through the center of force. All right. So this is 13.3 in the Gold edition, in the third edition of Golds. And as far as I can tell, the audio is looking okay. Let me know if there's any audio issues. And I think I have room to expand the screen just a little bit. Like so. And we'll have it like that. All right. So I think I need to scroll through the book for this to remind myself what's going on. You all recall we read through the book and got to the virial theorem, which is 3.4. There's 10 sections to this chapter, so we definitely didn't get through half the sections. But let's see if we can have an idea of what's going on. One thing about this book, it scrolls when you scroll through pages. The one thing we know is, if I recall, E4 is circular. So and E3, the energy is E4 at the minimum. The fictitious potential, as shown that the two bounds coincide. Motion is possible only at one radius. So we knew r dot equals 0. The circle, negative. Remembering that the effective force is the negative of the slope of the v curve. What prime is for circular orbits is simply that f prime be 0 or fr equals negative L squared over mr cubed, which equals negative mr theta dot squared. We have here the familiar elementary condition for a circular orbit, that the applied force be equal and opposite to it, the reverse effective force of centripetal acceleration. Properties of circular orbits and the conditions for them will be studied in greater detail in section 3.6. So why don't we go to section 3.6? So that's what we did earlier. All right. So why don't I start going through the book here? Close orbits. Bertrand theorem. We have not yet extracted all the information that can be obtained from the equivalent one-dimensional problem or from the orbit equation without explicitly solving for the motion. In particular, it is possible to derive a powerful and thought-provoking theorem on the types of attractive central forces that lead to closed orbits, i.e. orbits in which the particle eventually retraces its own footsteps. So closed orbits repeat, to put it simply. So it'll eventually restart where it was and repeat its own cycle. Conditions have already been described for one kind of closed orbit, namely a circle about the center of force. Let's look at the problem again. Under influence of an attractive central force, like the moon around the earth, directed toward a point on the circle, which is where the particle is, then the force varies as the inverse fifth power of the distance. For any given L, this will occur. And notice, by the way, that the FR naught that they give here is the same one that we got earlier. Minus L squared over M R naught cubed, which is equation 3.40. For any given L, this will occur if the equivalent potential V prime R has a minimum or maximum at some distance R naught, and its energy E is just equal to V prime R naught. Okay, so any L V prime R has a minimum or maximum as min or max at R naught. And E equals V prime R naught. So that means that partial V over partial R, I should say partial V prime R naught. We'll write this better. Partial V prime R naught over partial R equals 0. So that means that there's a minimum or a maximum. So we know that from our calculus, that if you have a minimum or a maximum, the first derivative is 0 at that point, meaning the slope is 0 at that point. The requirement that V have an extremum is equivalent to the vanishing of F prime at R naught. Okay? Leading to the condition derived previously, which we saw. Now actually move this down. Actually, let me move this whole thing down. Or at least copy this whole thing. Which means that a force must be attractive for circular orbits to be possible. Makes sense? In addition, the energy of the particle must be given by E equals V R naught, and notice that's V not V prime, plus L squared over 2m R naught squared. That's 3.41. And perhaps we'll just keep this down there. Not sure if I need this for the problem. So what I'm writing as notes from the book, I'll eventually extract out and just turn the actual problem solution. Right, so I should be fine without that. By which by equation 315 corresponds to the requirement that for a circular orbit R naught is 0. Okay. Okay, so that makes E. So if R naught is 0, R naught is 0, doesn't this not make sense? Well, we'll keep going. We'll see. Why don't we fill out equation 3.15? Right. So 3.15 is 1/2 m R dot squared plus 1/2 L squared over m R squared plus V equals constant 3.15. Half m R dot squared plus 1/2 L squared m R squared plus V equals constant 15. But I made a note on my page. There we go. Page 89. Which, by equation 315, corresponds to the requirement that for a circular orbit, R dot is equal to 0. Or not R, but R dot. Equations 340 and 341 are both elementary and familiar. between them, they imply that for any attractive central force, it is possible to have a circular orbit at some arbitrary radius r, provided the angular momentum L is given by equation 340 and the particle energy by 341. So these two things are vital components of this problem. L must be given by 340, so if we solve 340 for L, that has to be true. And the energy has to be like so. The character of the circular orbit depends on whether the extremum of V prime is a minimum, as in figure 3.8, or a maximum, as in figure 3.9. Come on now. So 3.8, it's a minimum. And 3.9, it must be upside down the curve. Yep. All right. If the energy is slightly above that required for a circular orbit at the given value of L, then for a minimum in V prime, the motion, though no longer circular, will still be bounded. However, if V exhibits a maximum, then the slightest raising of energy, above the circular value 3.34 results in a motion that is unbounded, with the particle moving both through the center of force and out to infinity, with a potential shown in figure 3.9. Let's find equation 3.34. We're at 3.34 as well. SD full d squared u over d theta squared plus u equals negative m over L squared full d du of potential V times 1 over u. So this is 3.34. So of course, borrowing the terminology from the case of static equilibrium, the circular orbit arising in figure 3.8 is said to be stable, and 3.9 is unstable. The stability of the circular orbit is thus determined by the sign of the second derivative of V prime at the radius of the circle being stable for positive second derivative, unstable for V concave down. A stable orbit therefore occurs if second derivative of V prime at R naught equals negative partial F partial R plus 3L squared over MR to the fourth naught is greater than 0. All right. So circular orbits, partial F over partial equal to R naught is less than 3 F R naught over R naught 4. They give a different form. For D L D L R equals R naught is greater than negative 3.43 prime. Where F R naught over R naught is assumed to be negative and given by dividing equation 340 by r naught if the force behaves like a power law of r in the vicinity of the circular radius r naught. Right. So we also have F equals negative K R N, power law. Then the stability condition becomes stability negative K N R minus 1 is less than 3 K R N minus 1, or N is greater than negative 3, where K is assumed to be positive. A power law attractive potential varying more slowly than 1 over r squared is thus capable of stable circular orbits for all values of r naught. Okay, and it has to be an integral greater than right, basically they're taking the attractive potential. So this is the power law attractive potential. No, hold on. This is the attractive force. Mhm. So if we were to put n equals negative 3 here, that's 1 over r cubed. If we put in negative 2, that's 1 over r squared. So it needs to be greater than negative 3, so it's going to be negative 1/2 or negative 1. K is assumed to be positive. If the circular orbit is stable, then a small increase in the particle energy above the value for a circular orbit results in only a slight variation of r about r naught. It can be easily shown that for such small, so now let's go into the deviation thing. So let's look at the question again. We need to show that a variance is an inverse fifth power of the distance. The book says that L L must give 340. You give him about 340. So we can say F R naught M R naught cubed equals negative L squared. Now just move V negative now. L equals square root of negative F R naught M R naught cubed. Maybe I'm thinking about this incorrectly, and I can't do this just from the equations. Maybe I need to solve it like Lagrangian. If the circle orbit is stable, it can be either shown that for small deviations from the circular conditions, the particle executes a simple harmonic motion in u equals 1 over r about u naught. Here, a is an amplitude that depends on the deviation of the energy from the value of the circular orbits, and b is a quantity arising from a Taylor series expansion. Professor did this in class. Of the force law Fr about the circular orbit radius r naught. Direct substitution into the force law gives that as the radius vector of the particle sweeps completely around the plane, u goes through b cycles of its oscillations. If b is a rational number, the ratio of two integers, p over q, then after q revolutions of the radius vector, the orbit will begin to retrace itself, so the orbit is closed. So a slightly eccentric orbit is still closed. So this is taking us to Kepler's laws. It's energy for a circle. Okay. Another condition for circular orbits that we get from in 3.7. I'm trying to find all the things related to circular orbits. The Kepler problem. Kepler m squared. Inverse square law is the most important of all the central force laws, and it deserves detailed treatment. So that if a particle describes circular orbit and inclusion of attractive central force, directed to a point on the circle, then the force varies as the inverse fifth power of the distance. The inverse square law is the most important of all. For this case, the force and potential can be written as, so we have F equals negative K over R squared, and V equals negative K over R. There are several ways to integrate the equation for the orbit, the simplest being to substitute 3.49 and the differential equation for the orbit 3.33. Another approach is to start with equation 3.39 with n sets equal to negative 2 for the gravitational force, where the integral is now taken to be indefinite. The quantity theta dot appearing in 3.50 is a constant of integration determined by the initial conditions that would not necessarily be the same as the initial angle theta naught at time t0. The indefinite integral is the standard form. You can get that from a table of integrals with these substitutions. Orbit, right? The constant of integration can now be identified from 3.55 when the turning angles in the orbit. Note that only 3 of the 4 constants of integration appear in the orbit equation. This is always a characteristic property of the orbit. In effect, the fourth constant locates the initial position of the particle on the orbit. If we're interested solely in the orbit equation, this information is clearly irrelevant and hence does not appear in the answer. Of course, the missing constant has to be supplied if we wish to complete the solution by finding r and theta as functions of time. Thus, if we choose to integrate the conservation theorem for angular momentum by means of 3.55, we must additionally specify the initial condition, the initial angle theta naught. Now, the general equation of a conic with one focus is at origin, where E is the eccentricity of the conic section. By comparison, the nature of the orbit depends on the magnitude of E according to the following scheme. Right? So we're dealing with a circular orbit. So E equals negative mk squared over 2L squared. Eccentricity equals 0. This classification agrees with the quantitative discussion of the orbits on an energy diagram. All right, so for a circular orbit, can v are constant equals t plus v equals negative v over 2 plus v equals v over 2. Hence equals negative k over 2r naught. From 3.41, the statement of equilibrium between the central force and the effective force, we can write k over r naught squared equals L squared over m r naught cubed, or r naught equals L squared over m k. Thus, E equals negative m k squared. Also, they're just showing the derivation of that. The above condition for a circular orbit. Gotta go into elliptical. So they can hit the, what's we call them? There we go. L equals m r squared theta dot equals m r v theta equals m a squared theta dot naught equals m a v naught. For the conservation of angular momentum in the elliptical orbits of seven major axis A and a circular radius A. All right, so I'll take a look and see if I can somehow progress on getting this attractive central force. I was hoping I can perhaps use this but also take this again, L is going to give me FR. So it seems to be something to do with this. Again, L squared. I'm going to swap out L squared. What can I swap that out for? Okay, no, but I had something for a moment. So L squared equals AMR. Squared equals R naught M K. That doesn't help. Right, I have to look at this. Theoretically, the answer is going to be somewhere in these early chapters. I try looking at the derivation before I move to something else. It varies as an inverse power to the third. Maybe the detail is that it's sand directed toward a point on the circle. You'll look at this later and read it more closely. Seems like it's so close. There's just one thing I need to. Seems like there's just one thing to substitute up in here to get that. Uh, I'm not sure what it is to substitute though. Like a substitute for M. That still won't give me, there's only one R in the denominator. So M equals L squared K. L squared is that. So M equals R naught. Give me the same thing back. Right. I'll just hold off and come back and look at this one. But whenever I figure this problem out, I'll come and show you what I got. It seems like it's to do with these. It seems like the best thing to do may be just to do the derivation again for the this derivation here to get the Lagrangian and then get the equations of motion, which take a look at that now and see just in case. So these are the derivations, but I remember seeing a force equation here. I know we can do the Lagrangian with multipliers. I mean, the only thing I can think of is if we did a Lagrangian with multipliers. So if I do a Lagrangian with multipliers, it'll end up being d dt partial L over partial Q dot I minus partial L over partial QI, and then it'll be plus lambda partial F over partial Q I. Is it QI or Q dot I? Let me remind myself. Let me search multiple. Actually, I don't know if search works here. Multiplier. No. So, if I'm recalling correctly, if I did a Lagrangian with the multiplier, that would do it. Let's try to find the full equation again. The constraint equation. Right. This book is I just need to read it more often. Maybe is that what it is? Like I know what equation I'm looking for, but it seems like exceedingly hard to find. Just like a simple rendering of the equation I'm looking for. So it's like as a plus. This is what I was looking for here. Hate when that happens. It is plus a lambda that equals 0. So I'm looking at that properly. What I should do is just finish those previous problems I was looking at, and I'll come back and look at this again. Actually, the previous, I'll take a quick break. I'll come back and finish working the series of problems that I was working before. So I'll come back and do some Lagrange problems. One will be a double pendulum, and one will be a particle falling under the dissipation force of air resistance. So check back in about 5 or 10 minutes, and I should have that going. I'll see you all soon.